Wait. ¿Comienzo? So, okay, good morning, everybody. So it's my great pleasure to be here again in person in São Carlos after a long time. So thank you very much to the organizers for the invitation. So this is lecture 3 of the course about ICs, isolated complete intersection singularities. So I will start. So this is the summary of this lecture. So there will have two parts. In the first part, I will speak about the formations of ICs. We will see basic invariants, versal deformations, and then some analytic properties. And the second part, I will speak about the Milnor fibration, the topology of the generic fibers, the link of an isolated singularity, and we finish with a theorem by Gaffney and Hofstra. So I would like to say that the notes of this course, the 4 lectures, will be available at this link here. So at the moment, there is only this is not the final version yet, but there will be a final version. Then when we have a final version, I will send to Raimundo to put in the web page the link, okay? So in particular, this lecture 3, this is strongly based on Loyenga's book. This is a classical book on ICs, on isolated singular points of complete intersections. So I strongly recommend to follow this course to get a copy of this book, okay? So let's start. So the first point, I will review some basic invariants of ICs that some of them were already presented in the lecture 1 and lecture 2. So just to recall that an ICIS, an isolated complete intersection singularity, is a germ of complex space X, which is, on one hand, it is a complete intersection. So complete intersection means that the number of equations of the space is equal to the codimension. So in the hypersurface case, this is always the case. You have only one equation, but in general, the minimal number of equations is not the codimension. But when this happens, we say that it is a complete intersection. And it has also isolated singularity. Isolated singularity means that the singular locus as a germ is only the point X. By definition, the local ring of the complex space germ is this ring, which is On over the ideal, which defines the space. And then we see that any ICs can be seen as the fiber of a holomorphic map germ F, which components are the generators of the ideal. So this is a mapping from Cn to Cn minus small n. And this is K finite, which means that the K codimension is finite. And this follows from the geometric criterion. So remember that the geometric criterion says that a mapping F it is K finite if and only if F is finite to 1 on its critical set. The critical set, CF, is the set of points where the differential of F is not surjective. But this is equivalent to that F minus 1 of 0 intersection with CF is equal to X. This is as germs. But this is equivalent to the fact that F minus 1 of 0 minus X, is smooth of dimension n. This is X. This is by the Jacobian Criterion. But because this is Cn and Cn minus n, this is if and only if X is ICs of dimension n. Okay? So here, this is the converse. Conversely, the fiber of any k-finite map germ is an ICs of dimension n, again by the geometric criterion. It's here. And moreover, the local ring of the ICs X coincides with the local algebra of F. So recall that this object Q of F was defined. Q of F was defined as the ON quotient, the ideal I defined by the components of the mapping. So by definition, the local algebra is equal to the local ring of the ICs. So I don't know why in algebraic geometry or in analytic geometry, it's called a local ring, and in the language of mappings, singularities of mappings, is called local algebra. I don't know why, but of course, you have an isomorphism of local rings. This gives an isomorphism of local algebras, and conversely, any isomorphism of local algebras gives an isomorphism of local rings. So it follows that two map germs. No, this is another theorem that was shown in the lecture 1, that two map germs F and G are K equivalent if and only if the local algebras are isomorphic. So as a consequence, we get that we have a bijection between the set of isomorphism classes of ICs embedded in Cn and dimension n, and the set of K classes of K finite map germs from Cn to Cn minus n. Okay? And the isomorphism is given via the local ring or the local algebra of the mapping. Okay, so if you have any question, please stop me and ask me. Don't be. Okay, so one remark is that sometimes we have one ICs which is embedded in some ambient space, and you have another ICs which is embedded in a different ambient space. So no problem, because after taking translations, for simplicity, we can assume that the points are the origin in the ambient spaces. And then if X is the fiber of some mapping F and Y is the fiber of some mapping G, then instead of F, here we assume capital N is less than or equal than capital M, and then we can substitute F by the constant unfolding, which is F times the identity. So now we can apply the same criterion. So X and Y are isomorphic if and only if F times, oh, sorry. Oop, what happened? Oop. Here. Okay, so X and Y are isomorphic if and only if F times the identity and G are K equivalent, okay? Well, given any ICs given by the fiber of a mapping F, which is K finite, we can define this OX module, which appeared yesterday in the lecture by Matthias and Anne, which is called the T1. So T1, by definition, is the quotient of the module OX to the power n minus n, quotient by the submodule defined by the classes of the partial derivatives. So here we take the classes of the partial derivatives, and we take the submodule. But recall that the K-tangent space, so theta F can be identified with On to the power n minus n, and the k-tangent extended space of F, by definition, is On, the partial derivatives, plus the ideal I times On n minus n. So because we have this here, then it follows that we have an isomorphism like this. So the T1 can be identified with this normal space to the orbit for the K equivalence. And the dimension of this module, the C dimension, because F is K finite, this module has finite dimension over C, and the dimension over C is called the Turing number. So it is equal by definition to the extended K codimension of F. So this gives the link between the invariant of the ICES and the invariant, the infinitesimal invariant of the ICES and the infinitesimal invariant of the map. Of course, we have to introduce here a definition, because if you have to compare two such modules for two such ICES, then one module is defined over one ring and the other module is defined over a different ring. So if you have a M and R module and N is an S module, an isomorphism between M and N will be a pair phi L, where phi is a ring isomorphism and L from M to N is an R module isomorphism, where here we consider N as an R module via phi. Then it follows, this lemma is important, that if two ICES are isomorphic, then there exists an isomorphism between the T1 modules, the T1 module of X and the T1 module of Y, where this is an isomorphism in the above sense. Okay, one more invariant, which is important, is the so-called reduced Kodaira-Spencer mapping. So by definition, given F, rho F is the mapping from the tangent space to Cn minus n at the origin to the T1, and is given by this definition. So rho F of a vector, a tangent vector V, is the residue classes of the composition composed with F, where this is a vector field which is an extension of the tangent vector. So take any vector field such that at the origin is the tangent vector, and then composed with F, this gives a vector field along F. So just take the class of this. So an important theorem is that the Kodaira-Spencer map, rho F, is surjective if and only if the mapping F is A stable. So the notion of a stable map appeared yesterday in the lecture 2 by Professor Ruas. Okay. So one important thing is that the Kodaira-Spencer map is not an invariant of the ICES. It depends on the choice. Depends on the choice of the mapping F. Okay. So some exercises for this part. So the first one is we consider F and G from C2, the plane to the plane. The first one is F of xy, xy cubed plus xy. And the second one is G of xy, xy cubed. So we can see that F and G, they are K finite, both, and they define the same ICES of dimension 0. And moreover, in this case, the Turing number is 2. But for the first one, the Kodaira-Spencer map is an isomorphism, so F is stable. This is not difficult to see. And for the second one, the Kodaira-Spencer map is not surjective, so G is not stable. So in particular, the Kodaira-Spencer mappings are different. So this shows that it depends on the choice of F. Nevertheless, we have some kind of invariance when we take A equivalence instead of K equivalence. So this is another exercise that if you have two maps, G, F and G, which are A equivalent, you have such a commutative diagram for the Kodaira-Spencer mappings, where here the rows are isomorphisms induced by the A equivalence between the maps F and G. Okay. And finally, this is one more exercise that any ISIS is isomorphic to the fiber of a K-finite map germ of rank 0. And in this case, this N is usually called the embedding dimension of X. Okay. So let's go for the second part of this first part. So this is about versal deformation of ISIS. So in lecture 2 yesterday, so Sidinia told about versal unfolding and versal deformations of mappings for the contact group K. So here we will see the analogous concept for ISIS, and we will see that both concepts are strongly related. So basically, the versal unfoldings of the mappings is the same as the versal deformation of the ISIS. So by definition, deformation of an ISIS x0 at a point x0 is a pair iota F, where F is a mapping, is a holomorphic mapping between smooth spaces X and S, such that the difference of the dimension is the dimension of the ISIS, is N. And iota is an isomorphism from x0 to the fiber of the mapping. So the isomorphism has to be understood as isomorphism of germs of complex spaces. So the corresponding local rings are isomorphic. So roughly speaking, what we are doing here is that we take, when we define an ISIS, we take a mapping like this, but we want to do it in a coordinate-independent way. So it's better to consider a general F from a general manifold X and a general manifold S. And the only condition is that the difference of the dimension is the same, is N, and the fiber, of course, is isomorphic to the ISIS. So in particular, this is an advanced comment. In particular, this implies that this mapping is flat, which is a non-easy notion in algebraic geometry. Because in general, if you have a singularity which is not an ISIS, which is a general singularity, then you can also define the notion of deformation, but that definition is more general. You have to assume that X is not singular, is possibly singular, that S is possibly singular, but you put the condition that F is a flat mapping. This is for the general theory of deformations. But for ISIS, it's more convenient to assume that these X and S both are non-singular. And this gives the flatness of the mapping. Okay. So the second definition is the notion of a morphism between one deformation and another deformation. So this is a commutative diagram like this, so that this diagram is Cartesian. So Cartesian means that the diagram is commutative, and moreover, so a diagram like this is Cartesian. I put only the space for simplicity. So Cartesian means that this is commutative, and if you have any other space and mappings here which make the diagram commutative, then there is a unique mapping here also which makes the diagram commutative. So an equivalent way to see this is that this space here, this X prime, is the fiber product of these two and this one over this one. This is an equivalent notion, okay? Well, a deformation is called versal if for any other deformation there exists a morphism G and G tilde from the second to the first one, okay? In general, here we do not require the morphism to be unique in any sense. However, if the differential is unique, then we say that the deformation is miniversal, okay? Well, one thing is that if we have any deformation, f, iota f, and we have an A equivalence phi and psi between f and another f prime, then we can construct a new deformation. A new deformation, iota prime, f prime, where iota prime is, sorry, this is iota prime, should be here. It's a mistake. This is iota prime missing here. And then this gives a new deformation. In particular, if we take coordinates, then this shows that any deformation is isomorphic as a deformation to a deformation of the form iota prime, f prime, with f prime in this format, in the format where you have not a manifold, but you have Cn here and Cn minus n here. Okay? Well, and the main theorem of this part is the following, is that if we have an ISIS x0, x0, then first, the deformation iota f of x0, x0 is versal if and only if the Kodaira-Spencer map rho sub f is surjective, okay? The second point of the theorem is that two versal deformations of the ISIS are isomorphic if their base germs have the same dimension. If S and S prime have the same dimension, and the two deformations are versal, then they are isomorphic. The third point is that any ISIS admits a miniversal deformation, and any two of them are isomorphic. And finally, that a deformation is miniversal if and only if the Kodaira-Spencer mapping is an isomorphism. Okay. Okay, so because of this theorem, we have a corollary is that if x0 is an ISIS given as the fiber of a k-finite map germ f, and we take an unfolding, an R-parameter unfolding of f, then the following statements are equivalent. First, that iota f is a versal deformation where iota of x is x0. Second, that f is A stable as a mapping. And finally, that tilde f, which is x f tilde f, is just the graph deformation of f. This is a k-versal deformation of f. So the equivalence between 2 and 3 was given yesterday in lecture 2 by Siriña. And the equivalence between 1 and 2 follows from the theorem, because from the theorem, this is because of the first point, because deformation is versal if and only if the Kodaira-Spencer mapping is surjective, but the Kodaira-Spencer mapping is surjective if and only if the mapping F is stable. So the equivalence between 1 and 2 is given by this point 1. Okay? Well, the construction of F was also explained yesterday in lecture 2 by Roberta, and is based on Mather's algorithm. So by the exercise, we can assume that the mapping F has rank 0. So we have capital N is the embedding dimension of the ICs. But this implies, of course, recall that we have this definition here. So if the mapping has rank 0, all these partial derivatives are 0 at the origin. So all these partial derivatives are included in the maximal ideal times theta f. And the same happens here. All the functions fi, all of them belong to this ideal. So this also belongs to mn times theta f. So when f has rank 0, we have this inclusion here. Yeah. Now we take G1, GR elements of vector fields and theta f, whose residue classes give a basis as a C vector space of this quotient, mn times theta f, quotient the tangent space. Then this unfolding, this R parameter unfolding, capital F, given in this way. So fu of x is nothing but f of x plus the linear terms constructed with the functions gi. So this mapping is A-stable. And it follows as a consequence of the Theorem number tau is equal to n minus n plus the number of parameters here, plus r. So Theorem number is n minus n plus r. So this is the way to construct a stable mapping, or equivalently, a versal deformation of any ICs. Okay? So here we have an example. So this is a mapping F from C3 to C2 is given by x squared plus y squared plus z squared on the first component, and the second component is xy. So this appeared yesterday in the lecture by Matthias and Anne. So this is called the S5 singularity. So it is a curve. It's a curve in C3. So it is not a hypersurface, it's a curve. So we compute the tangent submodule. So the tangent submodule is the submodule of O3 squared generated by the partial derivatives. These three are the three partial derivatives of the mapping. And we have also to add the submodule, which is the ideal I times O3 squared. Okay? Now, we have to compute a C basis of this quotient, the maximal idea M3 times O3 squared over this tangent space. But this can be done easily with using singular, or of course you can use Oscar if you prefer. But so I promise that from now on I will try to use Oscar. So this gives a basis of this quotient. This is y0, 0y, and 0z. And then a mini-versal deformation of the ICs given by the fiber is iota f, where iota of xyz is xyz0, and capital F is this mapping from C3 times C3 to C2 times C3, and you only have to add these linear terms, y1, y, u1, y, sorry, u2, y, and u3, z, and that's all. You have the stable mapping or the versal deformation. Okay. So if you want to use the classical theory of deformation of singularities, then this is very complicated because you have to use very sophisticated objects in commutative algebra. To define the T1 or so on, you have to use very sophisticated objects. But if you use the mapping and And the K group, this is very simple, okay? And this can be implemented very, very easy in Oscar or in Singular, okay? Okay, so let's go for the final part. Sorry, in this case, of course, Theorem number is 5. Theorem number is 5. We will see that the Milnor number is also 5, and this is the reason that this is called the S5. This 5 here is related to the Milnor number, which in this case is the same as the Theorem number. Okay. So let's go for the final part of this. Here there are some exercises. So the first exercise is that if you have any deformation, then you can construct new deformations which are isomorphic just by taking A equivalences. So if you have any A equivalence given by a pair phi psi is an A equivalence between F and F prime, then you can construct a new deformation which is isomorphic to the first one, okay? And the second exercise is to compute versal deformations and the Theorem numbers of these two ICs. In the first case, we have zero-dimensional ICs given as the fiber of x cubed y squared. And this is a small variation of the S5 singularity. In fact, it is the S6 singularity. Okay, this is x cubed plus y squared plus z squared xy. Okay. Okay, so let's go for the final part of this first half. So this is I'm going to show a very nice theorem that was proved by Lujenga, and it is a byproduct of the theory of versal deformation. So by definition, given a germ of any analytic subset Z in Cn, so if we take a vector field in the ambient space, Xi, it is called logarithmic for the analytic subset if when you take any function of the ideal of the subset, then the derivative of this function by the vector field also belongs to the ideal. Okay? So for any h which is in the ideal of z, the derivative of h by Xi belongs to the ideal. So this notion of logarithmic vector fields was defined by Saito, and it is usual to denote the subset of all logarithmic vector fields by this term of minus log of z. So some basic properties. The first one is that it is possible to prove, it is not trivial, but it is possible to prove that a vector field psi is logarithmic for z if and only if psi is tangent to the set at any regular point. So at any regular point, you have a well-defined tangent space. So this vector field is tangent, so belongs to the tangent space at this point. Another interesting property is that this set is in fact an ON submodule of the module of vector fields on Cn. So this is a submodule. And another interesting definition is the notion of free divisor. So in algebraic geometry, a divisor is a different way to say a hypersurface. So a free divisor is a hypersurface such that this logarithmic vector fields, this is a free module of rank n. When this module is free, this is called a free divisor. Okay. This notion was also introduced by Saito. This is an important definition. Okay, so what happens when we consider a mapping F from Cn to Cp, which is k finite? Then because it is k finite, then if you have f from C and to Cp, which is k finite, yes? Okay. So k finite means that the k codimension of f is finite, and equivalently that f is finitely k determined. So the geometric criterion says that this f is finite to 1 on the critical set. But then we can use the Remer theorem, by Remer's theorem. This implies that the image of the critical set, which is the discriminant, this is analytic. So in general, the image of an analytic set by an analytic mapping is not analytic, but if the mapping is finite, then you have this Remer's theorem, which is that the image is analytic, okay? So by definition, this is called the discriminant. This is the discriminant of F. It's here, discriminant, okay. Okay, so the first lemma is that in general, for any k finite map germ, then this discriminant, which is analytic, is a hypersurface in CP. So this is true for any k finite map germ, okay? So it is a divisor. So a hypersurface is a divisor. But the main theorem is that when you have a stable map, when you have a versal deformation of the axis, which is an unstable map, then the discriminant is a free divisor. So the module of logarithmic vector fields is a free module of rank P. So this fact is very important. This, in fact, is the crucial step in the proof of a famous conjecture by David Mond that the discriminant, that the A codimension is less than or equal to the image Miller number or the discriminant Miller number. So for the case of mappings from Cn to Cp for n greater than P, this conjecture was proved by Damon and Mond, and this is the crucial point of the proof, is this theorem. And this theorem was proved by Lojenga in his book. Okay. Okay, so this is the end of the first part. So there are 5 minutes left, but I think it's a good point to finish here, okay, to have the break. Okay, thank you.
Any question?
Thanks for a nice talk. Can you give some intuition as to when a hypersurface is a free divisor? What is it about the geometry of the hypersurface that makes it possible?
Yeah, that's a good question. That is not easy to answer, but what is well known is that in general, a plane curve is always free divisor. So if you take sorry. So plane curve. So you can assume, for instance, that you have a plane curve given by f of x, y equals 0. And for simplicity, you can assume that f is weighted homogeneous. Then if you look for vector fields, which are logarithmic, then, for instance, you can take this one. This is fy partial with respect to x minus fx partial with respect to y. And then it follows, this is trivial, that the derivative of f with respect to this vector field is 0, because you have fy fx minus fx fy. Okay? So this is one vector field which is always logarithmic. But because it is weighted homogeneous, you have also the Euler relation. The Euler relation says that the degree times f is equal to w1 fx plus, no, x, fx plus w2 y fy. This is the Euler relation. Then this shows that this vector field, which is w1 x partial respect to x plus w2 y. So this satisfies that epsilon of f equal df. So this is also logarithmic. And it is possible to prove that these two vector fields, they generate all logarithmic vector fields. And also they are a basis. They are linearly independent. So in this case, it is not difficult to see that this is a free divisor, because you have only two generators which are a basis of the module. In higher dimensions, it is not easy, but for instance, one thing that is true is that if the hypersurface has isolated singularity, this is not a free divisor. So a free divisor implies that you don't have isolated singularity. So in C3, for instance, if you look for surfaces in C3, so the transverse double point, this is a free divisor. The transverse triple point, this is also a free divisor, but for instance, the Whitney umbrella, which is stable, this is not a free divisor. So it's not easy to see the geometrical flavor of this definition. Okay. Yes, in fact, these are discriminants. These two are discriminants, but this one is not a discriminant. Yeah. Okay.
No more questions? Okay, let's thanks again.
Yeah.
Just an announcement, please.
Should we start? Yes. Okay, so let's go for the second half of this lecture. So the second part is for the topology of the generic fibers of the ICs. So in the first point, I will speak about the link of an isolated singularity. So in this case, this is not an ICs. So X is a closed analytic subset, which defines an isolated singularity. This means that we can have a neighborhood U such that X minus the point X is smooth of constant dimension n. Then we take a function, a real function R, which is the restriction of a real analytic function tilde R defined on U, such that the inverse image of 0 is the point X. So this implies that the origin in the real line is not an accumulation point of critical values of the restriction of R to X minus X. So the proof of this lemma is based on a result which is called the curve selection lemma. So by using the curve selection lemma, you can prove this. This is not difficult. And the curve selection lemma is a classical result in real analytic geometry. Yeah, it's okay. Then, by definition, if you have a function R as in the previous lemma, then we say that R defines the point X in X. And it is usual to have the following notation. So this X sub R minus less than or equal to epsilon is the set of points of X where the function is less than or equal to epsilon, and similarly for these other notations, okay? In fact, usually we take the function R as this function. This is the square modulus of the distance squares of X prime minus X. So the inverse image of 0 is, of course, the point X. In that case, then, this notation is nothing but the intersection of X with the closed ball or the open ball or the sphere. These are the Euclidean sphere, the Euclidean ball, or the closed Euclidean ball. But it's better to keep this a general function R. Sometimes this is also called a control function. And it's better to have this if you want to make it coordinate independent, because the choice of the Euclidean spheres depend on the coordinates and depend on the metric. So you have to choose coordinates and metric, and it's better to use a function which is coordinate independent, and it is also independent of the metric. So we recall that the cone on a topological space Z is this quotient space. You take the cylinder, which is Z times the interval 0, 1, and just collapse one of this Z times 0 to 1 point. So this is called the cone. So one first result is if you have this control function R, which defines the point in X, and take epsilon positive such that this set is compact and this restriction has no critical values in this interval. This is always possible because of the previous lemma. Then this X sub R equal epsilon is a compact real analytic submanifold of U, and we have a homeomorphism H from the cone on this compact submanifold onto the set X sub R minus less than or equal to epsilon, in such a way that we have a commutative diagram like this, where this pi is induced by the projection into the second component. So this is called the cone structure of X. So this gives a cone structure theorem. Well, in this notation, this submanifold X sub R equal epsilon is called the link of X at X. And we take the control function as the distance square function, then this epsilon is called a Milnor radius for x at the point x, and also the closed ball or the open ball or the sphere are called the closed Milnor ball or the open Milnor ball or the Milnor sphere. So here we have a picture. So this picture is taken from the final dissertation of my student, Alberto Fernandez. And this is the cone structure of the plane curve given by the cusp, x squared plus y cubed equals 0 in the plane. And here the link is the trefoil knot that you can see here. This trefoil knot is contained in the three-dimensional sphere. So here you can see how you have this cone structure. So the proof of this proposition is given by integration of vector fields. So you take a covariant vector field here, and then you can integrate the vector field. So this is called a radial vector field, and you can integrate it to get the homeomorphism. Okay. In fact, this homeomorphism is a diffeomorphism outside the origin, outside the point x. So if you remove the point x, this homeomorphism is a diffeomorphism. Okay. Okay, so let's see that the choice of the function, of the control function r and the epsilon is not important. So if you have two functions r and r prime, which define x in x, then there exists an epsilon positive such that the hypotheses of the previous proposition are satisfied for r and epsilon. And if you take any epsilon prime such that this x sub r prime less than or equal to epsilon prime is included in x sub r less than or equal to epsilon, then the hypotheses of the proposition are also satisfied for r prime and epsilon prime, and there exists a diffeomorphism from this set x. This is the cylinder between r less than or equal to epsilon and r prime less than or equal to epsilon prime. So there is a diffeomorphism from this cylinder into this product. So this is the link times the interval 0, 1, which maps x sub r equal epsilon onto one of this x r equal epsilon times 0, and the other to x r prime equal epsilon prime times 1. So as a corollary, we see that the diffeomorphism type of the link of x at the point x only depends on the abstract analytic set germ x at x. That is, it only depends on the C algebra OXX. So this follows because if you take one control function r for one of them, and you have a diffeomorphism phi, then you can take r prime as the composition of r with phi. And then this gives easily that the two links are equivalent. Okay? And then because of the proposition, this link is independent of the choice of the function r. Okay. Okay, so let's go for the second point. So we now introduce the Milnor fibration. This Milnor fibration already appeared in some other lectures. So here I will give a version which is adapted to the case of ISIS. So for the moment, I consider a more general setting that it's a gem f from x to ck, which defines an isolated singularity. So what does mean this? This means that we can choose representatives x, which is closed analytic in some open set U in Cn, and we can choose a representative of f from x to ck, such that at each point of the inverse image of 0 minus the origin minus x, this x is non-singular of dimension n plus k, and f is a submersion. Okay, so this is a little bit more general than the case when you have an ICs. So now we choose a control function R, which defines the fiber f-1 of 0 at x, and take epsilon such that the link is well defined for this f-1 of 0 at the point and epsilon. Because this is compact, this f-1 of 0 sub r equal epsilon, this is compact, and this is a submanifold, this is smooth, then we have a neighborhood S of the origin in CK such that the restriction of F to this submanifold, this is a submersion along this inverse image of S. Moreover, we can take S contractible. And then we introduce this notation. This X is the inverse image of S sub R, so intersection with R less than epsilon. The X bar is the same with R less than or equal to epsilon. And finally, this is the boundary. This is when R is equal to epsilon. More notation, so C of F, or C is the critical locus of F. X sing is the singular locus of X. X reg is the regular part. Now for each point S in S, we take the fiber, this is the closed fiber, or the open fiber. And more generally, if we take any subset A of S, then we put this X bar sub A. This is the X bar intersection with the inverse image of A, and the same for the open. D of F is the image of C of F, which is the discriminant of F. This is well defined, this is analytic. And finally, the restriction of F to X to S, we call it a good representative of F, and the same for the X bar. This is called a good proper representative of F. Okay, so usually we take the control function as the distance square function, and it is also common to take S as the open ball centered at 0 of radius eta. So in such a case, this is a good proper representative. It has this form. This is the restriction of F from the intersection of X with the closed ball and the inverse image of the open ball of radius eta to the open ball of radius eta with 0 less than eta, less than epsilon, less than 1, and analogously for a good representative if we take the open ball instead of the closed ball. So this is the standard way that you find this good representative in most of the books about minor vibration. But we will see that it is important to have this general setting if you want to prove that this construction is coordinate independent. So it's better to take a general function R and a general neighborhood S. So here this expression means that we have to choose first the epsilon small enough, and then once we have fixed the epsilon, then we choose eta small enough, but eta depending on epsilon. Okay, because if you go back to the definition of S, here. So we first take this epsilon, R equal epsilon, and then we choose S in depending on this epsilon. So the eta in the above expression depends on epsilon because of this. Okay. Okay, so the theorem says that with this notation we have first that the good proper representative is a proper map, and that the restriction to the boundary is a C infinity, is a smooth trivial bundle. So the fiber on the boundary is independent of the choice of a point S. Second one is that the critical locus is analytic in X and is closed in X bar. Moreover, the restriction to the critical set is finite. It is proper with finite fibers. Moreover, the singular locus of X must have dimension less than or equal to K. And in the regular part, the critical locus of F has pure dimension K plus K minus 1. As a consequence, the discriminant is an analytic subset of S, also of dimension K minus 1. So it is a hypersurface in S, if not empty, and moreover, if the CF minus the singular locus of X is dense in CF. So you don't have to worry about this, because in our case, when we take analysis, this X thing is empty. So this X thing has no importance. The 5th point is that this mapping from the pair given by this X bar sub S minus DF and the boundary into the complementary of the discriminant, this is a C-infinity fiber bundle pair, and each fiber pair, which is given by X bar sub S and the boundary, this is a complex analytic and manifold with boundary. And moreover, at each point of the regular part of X, this F defines an ISIS. So with the notation of the theorem, so by definition, the fiber XS, where S is in the complementary of the discriminant, this is called a Milnor fiber. And if you take the X bar S, then this is called a compact Milnor fiber. And moreover, the fiber bundle of the item 5, this is called the Milnor fibration. Usually, when you take the control function as the distance square function, and we take the open ball as the neighborhood S, then this Milnor fibration is given in this way. And the Milnor fiber is the intersection of X with the open ball intersection with the inverse image of S, where S is a point which is not in the discriminant. And the same for the compact Milnor fiber. So this Milnor fibration was considered for the first time by Milnor, of course, in the case of a hypersurface, and when X is smooth. And the next proposition shows that the Milnor fibration only depends up to the diffeomorphism of the germ F. Okay, I'm sorry that this part is a little bit technical, but there is no way. We have to understand this, okay? So what happens if we have two good proper representatives of the same germ? So we take F from X bar to S and F prime from X bar prime to S prime, two good proper representatives of the same germ. Then there exists a neighborhood T of the origin in the intersection of S and S prime, and a C-infinity diffeomorphism, capital H, from the pairs associated with the neighborhood T, which is the identity on a neighborhood of the critical set, and which commutes with the projection onto the neighborhood T. In particular, this H induces a diffeomorphism between the fibers, between the compact Milnor fibers. Okay. Okay, so with these propositions, we see that the Milnor fibration and the Milnor fibers are well defined and only depend on the map germ F from X to CK. That they don't depend on the choice of the control function. They don't depend on the epsilon. They don't depend on the neighborhood S. Okay, so let's go now to define the homotopy, to see about the homotopy type of the Milnor fiber. So in this case, we now consider an ISIS, X0, and we will see about the compact Milnor fiber, X bar S, which is given by a map germ F from a smooth variety X, which in this case is Cn plus K, to Ck. So the following theorem was proved first by Milnor in the hypersurface case and later by Ham in the general case. If we have any ICs of dimension n, I take a good proper representative F from X bar to S. Then for any S, so any fiber, not only the Milnor fiber, but any fiber has the homotopy type of a wedge of a finite number of spheres of real dimension n. So this X bar S has the homotopy type of Sn wedge Sn for some finite number of spheres. We use this theorem in the particular case of a compact Milnor fiber, which means that the parameter S is not in the discriminant. And in this case, we define the Milnor number of the ICs. So by definition, if we take an ICs of dimension n, the number of spheres in the wedge of the compact Milnor fiber, where here S is not in the discriminant, so this is called the Milnor number of x0 at x, and it's denoted by mu of x0x. Okay. So the numbers of spheres, so the homotopy type is for any fiber, but for the Milnor number, we consider a fiber which is not in the discriminant. Okay. Well, the first important property, so by the previous theorem, by the previous section, we know that the compact Milnor fiber only depends on the map germ F. But we don't know if it is independent of the choice of F, because for the same ICs, we might have different Fs. So two different Fs, they will be K equivalent, and then this first theorem is important. This is not trivial. So if we have two ICs which are isomorphic, then the Milnor numbers are equal. So this shows that the definition of the Milnor number is independent also of the choice of the map germ F. Okay? Question: how to compute the Milnor number algebraically? So if you were yesterday on the lecture by Matthias and Anne, they showed this, how to compute, but I will explain again, okay? So we start with an ICs of dimension n, which is the fiber of a K finite map germ F from Cn plus K to Ck. And then we know by the theorem that the discriminant is a hypersurface in Ck. So it has dimension K minus 1, okay? Then there is a well-known theorem in analytic geometry, which is called Nether Normalization, that when you have a hypersurface, then you can choose a line L, which is a line through the origin, such that the intersection of the line with the hypersurface is only the origin. So this is a consequence of the Nether Normalization. Then, after a linear change of coordinates in Ck, we can assume that this line is the line yk equals 0. Okay, we can choose linear coordinates in such a way. But this is equivalent to that the map F prime given by the K minus 1 first components, this defines an ICs X prime 0 of dimension n plus 1. So this is because the only critical point that you will have in the discriminant is given by this intersection, which is the origin. Okay. Then with these conditions, we have the following result, which is known as the Legroel Formula, because it was proved independently by Le and Groel. And it says that the Milnor number of the ICs X0 plus the Milnor number of the ICs X prime 0, which is given by the first K minus 1 components, this is equal to this dimension. This is the dimension as a vector space of the quotient of the ring of holomorphic functions in n plus k, quotient by this sum, the sum of these two ideals. The first ideal is I of f prime. This is the ideal generated by the first k minus 1 components. So we skip the last one. And j of f is the Jacobian ideal, which is the ideal generated by the maximal minors of the Jacobian matrix of f. So here we take all the components. So in the first ideal, we take only the k minus 1 first, and here we take all the functions. Then this Legroel formula, this allows us to compute the minimum number of any ICs by using a recursive formula. In fact, we can inductively choose generic linear coordinates in CK. So we first choose coordinates such that the y sub k is the line which intersects only at the origin, but you can proceed to choose the other coordinates. And this implies that for each L from 1 to k, this map germ, FL, which takes the first L coordinates, this defines an ICs XL of dimension n minus L plus k. Okay? So we can chase linear coordinates as that this is true always. So if you recall the lecture by Matthias and Anne yesterday, they defined this matrix, this random matrix, which is used to produce these generic linear coordinates. Okay? So you take the functions in such a way that one of the functions is a generic linear combination of the others. So this is the way that they compute yesterday. So with this notation, we have this formula that the minimum number of ICs is equal to this alternate sum, where you take all these dimensions, where here this is the ideal generated by the L minus 1 first functions, and this is the Jacobian ideal of the L first functions. So this alternate sum gives the minimum number. So this formula in the hypersurface case, k equal 1, this simplifies to this one, and this is the formula, the usual, the well-known formula for the minimum number of a hypersurface, which is equal to the dimension of the ring of holomorphic functions quotient by the Jacobian ideal generated by the partial derivatives of f. And another case which is interesting, which is very simple, is the case that the ICs is zero dimensional. So in this case, the formula for the minimum number can be simplified as follows. So for any zero dimensional ICs, the minimum number is equal to the dimension of the local ring minus 1. So this is because in this case, this local ring has finite, the crude dimension is 0, but this means that the dimension as a vector space is finite. And this minimum number is this dimension minus 1. Okay, an example which again is the same example as yesterday in the lecture by Matthias and Anne. This is the S5 singularity, but there is a difference because they consider the functions in a different order. So the xy was the first function, and x squared plus y squared plus z squared was the second. But because I am a smart person, I choose the right order, because in that case, if you take the first one, this defines a hypersurface with isolated singularity. So you don't need to choose generic linear coordinates. So in that case, you can apply directly the Legroel formula. So the minimum number of x prime is 1, and then the sum of the two minimum numbers is this dimension, but this dimension can be computed easily with singular with Oscar, of course, and this dimension is equal to 6. So the minimum number of the ICs of the line of the S5 singularity is 5. So the Miller number coincides with the Turina number and is equal to 5. Okay. So let's see some other nice properties of the Miller number. The first one is this property that I call the conservation of the Miller number. So this says that if you take any fiber, not a Miller fiber, but any fiber, you take any S. So for the Miller fiber, you take an S which is not in the discriminant, but here I take any S. So because you take any S, this fiber XS, this is not smooth. You might have singular points. Okay. So this formula says that the Miller number of the ICs is equal to the sum of the Miller numbers of the fiber at all singular points plus this term beta n of the compact fiber. But this beta n is the nth Betti number, which is nothing but the number of n spheres in the wedge. Okay. For instance, imagine that you have you take the cusp. For the cusp, the cusp is x3 plus y squared equals 0. So here the Miller number is 2. Then the Miller fiber, so you can take this fiber which is not a Miller fiber. You have here, this is, and then here, this is a Morse point which has Miller number equal 1. But here, you have here some bubble here. So this bubble, the Betti number is equal to 1. So here, this has beta 1 equal 1. So the sum of the two gives 2, which is the Miller number. Okay, so this is an example of this formula. Okay. So in general, the Miller fiber is not this. Miller number is something like this. So this picture is a little bit, this is not a real picture because, well, this is a real picture, it's not a complex picture. In the complex picture, you have something like this, which has beta equal to, okay? Okay, so one corollary is the upper semi-continuity of the Miller number. This is because all terms here, all of them are greater than or equal to 0. This is the number of spheres. And these Miller numbers are greater than or equal to 0. So it follows that for any S in S and for any X prime, the singular locus of XS, the Miller number will be less than or equal than the initial Miller number. So the Miller number cannot be greater. It has to be less than or equal. Okay. Using this upper semi-continuity, it is possible to prove this theorem. This is not trivial, but this is possible to prove, is that given any ICs, then the Miller number is equal to 0 if and only if the ICs is smooth. So if you have a singular point, then the Miller number will be always positive, not 0. So when you have an isolated, you have an ICs with a singular point and you take the Miller fiber is not contractible. You have some topology always, okay? And then as a consequence of the conservation of the Miller number and of this theorem, you have this corollary, is that if at some point you have the equality of the Miller numbers, if you have some S and some X prime such that you have equality, then this is the only singular point, because all other, the Milnor number, because of the formula, the Milnor number will be 0, and because of the theorem, if the Milnor number is 0, then the ISIS is the ISIS is smooth, so you don't have singular point. Okay. Well, and then I will finish. See here, this is an exercise. Compute Milnor number of these two ISIS. This is zero-dimensional ISIS, and this is the S6 singularity. Okay, so you can guess which is the solution of the exercise. Okay, so let's go for the last part of my lecture, which is about the Gaffney-Hofstra theorem. So Gaffney and Hofstra showed a very general theorem, which states, roughly speaking, that if two germs of complex spaces, X and Y, they have isomorphic singular loci, this is in some specific sense, then the two spaces are isomorphic. Okay. So here we present a simplified version in the case that X and Y are ISIS. And the case of hypersurfaces with isolated singularity, this was obtained previously by Mather and Yao. So the theorem says that if you have two ISIS, X and Y, which are given as the fibers of K finite map germs, F and G, respectively, assume that there exists an isomorphism phi L between the T1s, between the T1 of X and the T1 of Y, for some isomorphism phi, then the two ISIS are isomorphic. Okay, so here, this is an isomorphism phi which comes from a diffeomorphism from Cn to Cn, but of course, this diffeomorphism, in principle, this doesn't preserve the ISIS, because if not, the theorem is trivial. So you have to prove that, okay? So I think I have a pair of minutes. So I will give a sketch of the proof. So the proof is not easy, but I will sketch the proof. So for simplicity, we assume that X and Y are the origin in Cn. And by hypothesis, we have a isomorphism phi L between the two normal spaces for the contact equivalence group. We must show that F and G, they are K equivalent. So if they are K equivalent, then you know that the ISIS are isomorphic. So in the step one, we can assume that the two tangent spaces are not only isomorphic, but they are equal. This is not difficult. This is just substitute F by some different F, which has the same tangent space and which is K equivalent to F. In the second step, we take this family Ft, which is this is the line generated by F and G. No, is 1 minus Tf plus Tg for any T. And then it is not difficult. This is simple to prove that the tangent space of any Ft is the same as the tangent space of F. So you have constant tangent space. So this is the more technical part. This is the step 3. Then you show that for a parameter, a fixed parameter T0, then you consider the unfolding capital F given by this family Ft. Then you show that this F is Ke trivial. So this means that there exists capital phi, which is an unfolding of the identity, and Lt, which is a family of matrices, of matrices, invertible matrices with entries in Cn times C, such that L0 is the identity, and you have this Lt times Ft composed with phi t is Ft0. So this means that the unfolding is Ke trivial. So as I said, this is the most technical part. So this, but the techniques are not standard techniques. You have only to integrate vector fields, and by means of integration of vector fields, you can find these unfoldings phi and LT. So in the notes you have all the details. Okay. And finally, the step 4 is that on one hand, by the step 3, you know that for any t0, the germ of ft0 at the origin is k equivalent to the germ of ft at phi t minus 1 of 0 for all t in a neighborhood of t0. But this implies that the ISIS defined by ft0 at the origin is isomorphic to the ISIS defined by ft at the corresponding point, which is phi t minus 1 of 0. But because of the invariance of the Milnor number, this implies that the two Milnor numbers are equal. And then, by using the last corollary of the previous section, this implies that this is the only singular point. This point, phi t minus 1 of 0, this must be, if you have the equality at some point, then all other points are smooth. So this is the only singular point. Okay. But on the other hand, we have this by step 2, we have that the K tangent space is the same at any point. So this implies that 0 is a singular point of xt for any t, of course. And then putting together the two things, we deduce that this point, phi t minus 1 of 0, must be the origin. It must be the origin necessarily. But this shows that this unfolding F is not only K E trivial, but also K trivial. In particular, the K class of the germ Ft at the origin is locally the same. So this is locally constant, but since the complex plane is connected, then it must be globally constant. In particular, F0, which is F, and F1, which is G, they are equivalent. And this concludes the proof. Okay. Okay, so thank you very much. I will finish here. Okay.
Well, I want to ask you about the vector fields that you have mentioned in the proof of the theorem.
Yes.
Because you say that you integrate. Well, I want to ask you what is the form of the vector fields, that if you can integrate them, because that is usually so difficult to find the solution of the vector field.
Yeah, to find the explicit solution is difficult, but of course you have theorems that you say that you have the solution exists and it's a unique solution.
Yeah.
But you know that you have a solution and it is unique. But of course, to find the explicit solution is not a easy task in general. So in the notes you can see which is the aspect of the differential equations, because this is a little bit technical, but if you look at the notes, then you can see how are so this is a system of ordinary differential equations.
Yeah.
So you always have, you put
so you suppose the solution.
Yeah, the solution is okay. Yeah.
And another question, I want to ask you if, well, this part of the board, well, that is similar to a Hamiltonian differential system, but on the board.
Yeah, this is of course this is the Hamiltonian vector field associated to F.
But only for the curve.
Yeah.
But I want to ask you if there exists induced function. If you have this property, like a first integral, if you can find
in general. for a hypersurface in general.
Yeah.
No,
but-
it's not.
No,
This
but
only
if-
works in the case of a plane curve. In general, if you have
yeah.
more
Yes,
variables,
but-
you don't have that.
But if you can extend I don't know, the properties on this plane curve to other kind of curves
Yeah.
in a neighborhood of this curve.
Uh-huh.
I don't know if it is possible to find that kind of function.
I don't know. So in general, for hypersurfaces in more variables, it's not easy. It's not possible unless you have a free divisor. So for a free divisor, you have a nice structure. But in general, if it is not a free divisor, then it's complicated. Their log, the set of the module of logarithmic vector fields is a very complicated object. In general, it is not easy, and you have to use Singular or Oscar to compute them. It's not by hand. It's very difficult.
Okay. Okay. Thank you so much.
It's just a remark about the proof. It seems that all previous steps, up to step 3, you don't use the hypothesis that the germs are k-finite, right? Just in the last step. So even in step 1, for instance, and
Yeah,
yeah.
that's right.
So, but Terry's result is, does he use the hypothesis that
So maybe Terry can answer the question better than me. No, the theorem is more general than this. This is a simplified version for the case of ISIS.
Yeah, we really use it only in the last step because we really need to know that they're actually K equivalent instead of KE equivalent. And that was a useful trick, that the fact that the singularity, you can prove the singularities can't split using the ideas that Juano talked about. A historical note is that there were two threads in singularities in the early 60s. One was the Mather school, and the other one, we'll call it the French school. And a lot of information about hypersurfaces was done by the French school using the Jacobian ideal. And so the natural thing for them to try when they went on to ISIS was to look at the ideal of maximal minors of the Jacobian matrix plus the defining equations. But that turned out not to work very well. Instead, the other thread, which was Mather's thread, was the one which used K equivalents and using K equivalents to study deformations of sets. And so when you come to this Gaffney-Hauser theorem, I was convinced that you only needed to look at a finite dimensional vector space in order to get the results for ISIS, because all the information for the ISIS seemed to be concentrated at the origin. And in being a student of Mather's, it immediately came to me that we really should be using the extended K-tangent space, and that worked very well. And also we'll see tomorrow that the Legroel theorem, which looks like it's about ideals, is also actually about the Jacobian module. And we'll give a module form of the Legroel theorem tomorrow.
Okay.
So in the same way that you have a relation between for K finite germs, you have a relation between this and the ICs. But still the local algebra and the local ring, in general, they are the same object. So can you say something in general about varieties related to germs, not necessarily K-finite? Maybe if you have non-isolated singularity or something?
Yeah, the problem is with the codimension, because
Yeah.
when you have an ISIS, of course, the local ring and the local ring and the local algebra are the same. This is always true, but The problem is with the codimension, because you have, in general, if it is not k finite, in general, the fiber, the dimension is not n minus p. But you need this to have the equivalence between the two walls, between the wall of ICs and the wall of mappings. You need to control the codimension. But in general, if the mapping is not k finite, you don't have control about the codimension. The fiber might have any dimension.
Yes.
So in general, the dimension is greater than or equal than n minus p, because it is complex case, but it might take any value between n minus p and and n.
Yes,
Okay.
so you maybe you don't have a complete intersection, but
Yeah.
in general varieties, they are not complete intersections.
Yeah.
But for example, is there any relation between the resolution of singularities and these kind of maps? I don't know.
Sorry? Yes. Yeah, but you need some extra tool. For determinantal singularities, I think it's okay. You can have something similar.
You need to be in a good landscape.
Yeah, that's the point. So you have to control the deformations of the mapping or your object that you are taking into account. If you restrict the deformations to some special deformation, then it is okay. For instance, if you take analytic set, which is the image of a finite map germ, then it is okay if you take deformations which are images of all other a finite map germs. That's okay. Okay, any other question? Okay, thank you very much.
Mihai sent me his file, but I had to take off some proofs because it was too long and wouldn't fit in the 45-minute slot. But the file is the complete file is online on the conference website, and please check it out when after the conference maybe. Okay, so this what is this all about? As you can see here, the purpose of what I'm going to present today is to find a framework, to write down a framework in which you have vibration theorems and a very general framework, as general as possible. You have seen before, I mean, of course, it started with Milnor. We had hypersurfaces. That means we had functions defined on Cn with values in C. It was the C1 section about ICs. But the question is if you can go further than that and how far you can go and to work, for example, with real polynomial maps instead of holomorphic maps and so on. So this is the purpose of this talk, of this presentation, to set up this general framework in which you can prove vibration theorems. As a notation, K is going to stand again either for R or C. You have G, analytic map, could be real or complex depending on K. And M is greater than or equal to P. And as I said, for P equals 1, you have a Milnor's vibration theorem, classical Milnor vibration theorem. It works in C, but it works as in the same way over R. And because we want to go further, we assume that P is at least 2. It's greater than or equal to 2 from now on. And the remark here, because it appeared in Max exercise session and today in the morning, when you write the classical Milnor vibration theorem, it says that you have a vibration, but more than that, it does not depend if epsilon is small enough. If you choose a small ball, which is small enough, after that, after this threshold, the vibration itself doesn't depend on the radius of the ball. And it's important. If you didn't have that, you don't have anything. I mean, if you for every ball you had other vibration, I mean, what's the point? I mean, that doesn't make any sense. And this issue of independence on the choices of epsilon, delta, and this kind of stuff is going to be important. More than that, you talk about gems of functions, so let's say. The germ itself is not a function. It's an equivalence class of functions. It's very simple equivalence relation, but it's an equivalence relation. And whenever you work with an equivalence relation, you have to check that whatever object you define do not depend on the class, on the representative. Yeah, even when you're in college or something, you talk about groups, you take the factor, you have to check always independence on the representative. Yeah, this is the basic stuff that you learn once you learn about equivalence relations. Yeah, and this is as Mihai wrote here, this is an important issue, and we're going to look at this kind of issue in this talk. Mihai thought about this, and he has several papers that deals with this kind of this stuff. You have them here. Two of them are with Raimundo and Maiko, and two of them are with myself. So you have them here. And the first example where something strange happened earlier appeared in Bruna's Monday talk. So this is the function, the simple function from k squared to k squared. F of x and y is equal to x, comma xy. This function here is nothing else than the blow-up, the standard blow-up, written in a fine chart. Yeah, and you have the picture in your mind. The blow-up, you know what was the blow-up. More than that, Bruna drew a picture and you saw that in that picture, it was there are two colors, there are two pictures, in fact, one with the green and one with pink, if you remember, where she looked at the behavior of this map. This map for this map, we cannot define the image of the germ of the function. Yeah. And again, we had the picture. Okay. Then with this kind of phenomena in mind, first of all, I mean, when you decide that you want vibration theorems, the question is for what kind of maps you can get vibrations. And then, I mean, you have to put some conditions there. What kind of conditions do you put to get vibrations, to make everything work? Here, in fact, there are two definitions, but the first part is also a definition, but the first part is recalling a definition. You saw this definition again in Bruna's talk on Monday morning. The way that you define germs for functions, in the same way you can define germs of sets. You say that two sets have the same germ if you can find a small neighborhood of the origin, such that when you intersect this neighborhood with the two sets, you get the same thing. So it's the same story as for function. And then, if you have a map, you have the germ of a map G. Here is technically be continuous, but it doesn't have to be continuous. The same thing works also for non-continuous function, but it is continuous. You say that this, the image of a set in Km, G of A, is a well-defined set germ at this point at the origin, because we're working around the origin. It doesn't matter how you choose two small balls, one larger and the other one could be very, very small. When you take the image of the intersection of A with these two balls, so A intersect with B epsilon and A intersect with B epsilon prime, what you get, the two sets are going to have the same germ at the origin. And again, here in this equality, one of them, let's say epsilon prime, could be much, much smaller than epsilon. It doesn't matter. They are going to have the same germ. Yeah. So this is the definition. And kind of particular case, and somehow important, we say that the map is open at a point if whenever you choose, you have a neighborhood of the point in the source, the image is going to be a neighborhood of the point in the target. If this is the case, then it should be clear that G has a well-defined image as a germ. And here I want to make a distinction between open at a point and open in general as a topological map. If you talk about open sets, let's say that you talk about open sets between open sets, about open maps. Let's say you have two complex manifolds. These are complex manifolds. And you have a map here, F, which is holomorphic. For holomorphic map defined between complex manifolds, you have a very nice and simple criteria that tells you when this map is open. Now, this map is open. F is open if and only if, let's say that M has dimension M and N, small n. So F is open if and only if the fibers have dimension, pure dimension, of course, it's going to be pure, M minus N for every X in N. So holomorphic map is open if and only if all the fibers have the same dimension, the prescribed dimension, the one that you expect. This kind of stuff is not true if you talk about maps which are open at a point. And can I write here? I think they can manage. You have the following example. From C2 to C2, f of x and y is equal to x comma y plus x squared, no, times y plus x squared, y times y plus x squared. The fiber above 0 of this map has dimension 1, which is more than you expect. You expect dimension 0. Still, this map is open at 0. This phenomenon was noticed a long time ago by Alan Huckleberry in the 70s. But in one of the papers with Mihai, that I wrote at the beginning, we have a way to produce many examples. So there are many examples of functions that have, say, from C2 to C2, that have fibers of dimension 1, and they're still open at the origin. This condition, open at the origin, is not an open condition. The sense that you can find points nearby 0. So this is the function could be open at 0, but you can find points near 0 that are not open points. Yeah. Good. This is one remark. And the other remark is that if you talk about holomorphic functions, so if you talk about maps from here, from here to here, for such a function to have well-defined image, it turns out that it is equivalent to the fact that the function has the image of the function is actually analytic. It's a complex analytic variety. So the function is well defined even only if the image of the function is well defined as a germ, if and only if the image of the function is actually an analytic set. The proof for p equals 2 is in a paper of myself and Mihai, and in general it was proved by Helmut Hamm. But for maps from Rn to Rp, this is not true anymore. And you can look, for example, say R2, which is the same thing as C. We've already seen C, which is R2. And look at this map. Z goes to 1 plus Z times modulus of Z squared. This is a polynomial map. And it turns out, I mean, you could do the computations that this is well defined as a germ at the origin. The image is well defined. And still, I mean, here the image is not analytic. Good. What else can we prove? For example, we can prove that if you have a map with values in C2, and have a holomorphic, this is holomorphic, then the image of the singular set, I mean the discriminant, is actually a well-defined analytic set. However, this is not true for maps with values in C3. So, moral is that even if you have a well-defined image for the function, you don't know what happens with the singular locus. But it's clear that if you want to talk about vibrations and so on, you need to look at the singular locus. I mean, I don't think it's possible to do it otherwise. And then we have the following definition. So we say that a map is a nice map germ, and we abbreviate it NMG, if both the image and the image of the singular locus, the discriminant set, are well defined as germs. Yeah, so NMG stands for this type of stuff. And to have a cluster of examples is the class of ICs. So if you have an IC, that means you have a map from Cn to Cp, and the fiber has the right dimension, the expected dimension, and the codimension is equal to the dimension of the source. Then you have equality of germs, and if it happens that the singular locus intersects F inverse of the fiber just as 0, then this is a nice map germ. And you already seen more or less the proof, both Monday and today. So if this is the case, then you cut with a plane of dimension p of the base, and over there you have a finite map. Yeah. So this is the proof. And for the first part, the second part is when you can prove that actually the image of the singular locus, the discriminant, is not only a germ, but it's a hypersurface. And here is cited Ohenga books, but I think Juan talked about this kind of stuff in the morning, the first part. So this is stuff that you already seen. And so this is for holomorphic maps, but we have also a proposition for real maps. And over here you have a map from Rm to Rp. And if the singular locus of G's intersects the fiber just at a point, then G is a nice mapping germ. Yeah. And again, here we're not going to give the proof, but if this is just a simple lemma, just to give a feeling. So the lemma says that if you have a higher dimensional fiber, so this is the fiber, G inverse of 0. And you know that the singular locus is not the entire fiber, doesn't contain the entire fiber. And here I'm talking in terms of germs. But then what you can do, you can take points nearby, and doesn't matter how close, if you take a small ball around this point, you're always going to find points which are in the fiber, but not a singular locus. Over here, the map is a submersion, and the image of something open here is going to be something open around this point. So you always can find something here which is open and is mapped into something open downstairs. And this shows that the image of the map G, the germ of the image is actually the entire RP. This is a very simple lemma just for you to see something. But anyhow, you have the proposition over there. So you know that in this case, indeed, the G is a nice mapping germ. And then, of course, we have this notion of nice mapping gems, but we like something that implies maybe a stronger condition that will imply nice NMG, and at the same time to give us vibrations. And you remember the rho transversality condition, and you have the similar definition here. I mean, the definition of the Milnor set. Before I give you the definition, this is this remark over here that once that we have a nice mapping germ, the discriminant set is well-defined closed subanalytic set. Of course, it's well-defined. This is what the definition of NMG. But the main point that is actually closed. In general, if you have a polynomial map, the image of the singular locus is not necessarily closed. You can try to write examples by yourself. So in general, the definition of the singular locus is not closed. But if you assume that the mapping is nice NMG, then the discriminant is indeed closed and subanalytic. And now the definition of the Milnor set. Yeah, I think no, not I think. I know that you have seen it because I gave it here Monday afternoon. So you look at oops, I didn't write. Oh, but okay. So you have the rho. Let's say that rho is the distance function and is the norm of the point. And you look at the set of points of tangencies between the fibers of the function g and the spheres. So this set is the set of critical points of rho g, and you already seen this several times. And in fact, we are going to look at germs of this set. And now comes something more difficult, maybe. Well, it's not really more difficult, but this word stratification. I understood that you are going to hear tomorrow the definitions for stratifications, if I'm not wrong, tomorrow morning. And but already told you that the stratification is a splitting of your set, stratification for a set. You split your set in manifolds. You write it as the union of manifolds. Yeah. So this is the basic idea, and you can check the definition, the precise definition by yourself tonight. But tomorrow, I think you're going to hear the precise definition. In doing that, you can, even if your set is not very nice at the beginning, you split it in nice pieces. That's one thing. But it's not enough. This stratification, this cutting into pieces your set is not always enough. You need to know how they glue together. And I mean, this comes after working a little bit, and what normally is done, people work with the stratifications. These are conditions put in the place where the strata touch each other. Yeah, there are two conditions, A and B. I'm not going to give them now. It's not the markers, but keep in mind that stratification means cutting your set into smooth manifolds, and Winner conditions are about gluing them together. And suppose that you have a function, and suppose that you have here a stratification of the source. So in the source, you have a stratification, you have this manifold, and you can consider this Milnor set for each strata. And then what you do, you take the union of all these Milnor sets. And you call this one also the Milnor set of G, but it's stratwise Milnor set, if you want. And here I said about Winner conditions. If you try to prove that, for example, this set is closed, the original Milnor set, of course, is closed. I mean, the set of non-tangency is a closed set by definition. But in general, it's possible that this set is not closed. Once that you put this kind of condition, the Milnor set, this MG, becomes closed. Yeah. But without Winner stratification, you don't know that M of G is closed. So this is it's a handy. Okay, and now go ahead. Yes, so you restrict. You take say a strata. Now you restrict G to this strata. This is a sum manifold in some. It's not a closed sum manifold, but it's a sum manifold. It's a manifold. The function rho lives also on W alpha. Yeah. So this is, so you have here just a piece. Yeah. This is W alpha. You can restrict your function G but you can restrict also the function rho. Yeah, nobody stops you. And now you're on a manifold, you have the two functions, G and rho. Okay? So now the definition, you say that suppose that you have this function G. We already defined the notion of Milnor M of G, the stratwise Milnor set, and we say that the mapping G is tame. Yeah, this is the word tame. If we have this type of condition, that means, oops, I didn't break it, right? So if this is the fiber, that Milnor set can come like that. Yeah. So the fiber could be thick. The Milnor fiber, you don't know what happens here, but when you take the closure and of the Milnor set without the fiber, it is going to intersect the G inverse of 0 just at the origin. So this is the condition that is going to do the job for us, in fact. And I mean, this is recapping. We have in mind existence for vibrations. That's and if you look at the definition. From this definition, this definition implies that once we look at the strata of your stratification of low dimension, I mean dimension at most p, then dimension of the target, then the intersection with the fiber is going to be at most at a point at the origin. And you can hear, of course, that if you have a map, oops. Okay, sorry. If you have a map, so the fiber is just one point, this is, of course, satisfied. There's nothing there. And now, we can prove the following theorem. Suppose you have a map, and you suppose that it's tame. Then, the map is a nice mapping germ. And moreover, because I mean, you think about this strata, you assume a stratification, it turns out that the image of each strata is well defined. So not only the image of the function is well defined, but the image of each strata is well defined. And here, just a remark, two cases when the image is well defined. The first one is this condition when the singular locus of G is inside the fiber, and Massey showed that in this case the image of G is the entire target, and this is a consequence of the lemma that I said that I mentioned before, that if sing of G intersects G, the fiber, the central fiber, just in something that is more than the fiber, then you have also open image here. So, the idea is that this class of tame germs are the ones that are good for us. Yeah. But before I can state a vibration theorem, it's not enough, it turns out, to stratify the source. It turns out that you have to stratify also the target. And stratifying the target, I mean, is not new. This is kind of say standard, but once that you get to know what stratifications are. So this has been done before. You can stratify also the target. And I call this stratification S. And when you do that, you can do it in such a way that if you look at the discriminant set, you get this one is the union of strata. And more important, G is a stratified submersion. That means that if you look at the restriction from W alpha strata in stratum in W and the stratum in S, this map is a submersion. So maybe it's not a submersion in general, but we can cut into pieces the source and the target, and we get submersion. And WS is called the regular stratification of G. And now, in this context, so once that we have stratification for the source, W, stratification for the target, S, which are regular, which are good for G. You have a regular stratification WS for G. The definition says that G has a Milnor fibration if you can find small balls, one in the source, one in the source, one in the target, W epsilon, and usually the one in the target is taken very small so that everything goes fine. Once that you have epsilon, then you choose eta very small, such that when you take the restriction of G to the preimage of the small ball and you intersect it with the ball upstairs, what you get a locally trivial fibration, but it's a stratified one. It's a stratified locally trivial fibration, and it's independent of the choices that you made, epsilon and eta, provided that eta is small. And exactly what that means, first of all, when you say that it's a stratified locally trivial fibration, means that for each stratum in S, if you look above the stratum, you take the restriction of G to the pre-image of that stratum, what you get a locally trivial stratwise fibration. So on each stratum in the target, above it, you have a fibration. And the independency means that you start with epsilon and eta, and then you choose some smaller values, epsilon prime and eta prime. And the idea is that when you do that, think about this is everything stratified. In the smaller choices, the image is going to be the same as in the larger one. Yeah, then in the target we have the same strata. And moreover, once that you have the strata, the two fibrations above the strata are going to be diffeomorphic. Yeah, so they're equivalent. And with this definition and with this setting, you can prove that actually you do have two fibration. So if you have a polynomial map, a real analytic map, a germ of a map from Rm to Rp, and if you assume that G is tame, then you have a singular Milnor two fibration. So if it's tame, that means you can choose your stratifications, W and S, one for the source, one for the target. That makes these stratifications make G a singular two fibration. So this condition tends to together, of course, with all the machinery behind the witness ratifications and carefully choosing everything, makes things work. And I'll close with one application. This is a result that was proved before by Nicolas and Raimundo 6 years ago. And actually, it came from it's a question of Milnor in Milnor's book. Milnor formulated just for isolated singularities, but Nicolas and Raimundo did it in more general setting. And with our theorem, as a consequence of our theorem, you get this corollary. And so what was the point? You have a map from Rm to Rp, but you have row regularity. And then you take only the first p minus 1 component. Instead of p components, you take the first p minus 1 component. And then we have the fiber of M, of G, and the fiber of F. You have two maps, and you have Milnor fibers for each one of them. And the corollary says that the two fibers are homeomorphic. In fact, homeomorphic. The fiber of the other way around, yeah, the fiber of F is homomorphic to the fiber of G times an interval. Yeah. So, yeah. Okay. Thank you much. Questions?
So in this area, you always hear the name Tom's ratification.
No. It when you prove, you have to go to Tom's ratification, right? I mean, to Tom is isolated lemma. So that, yeah. So in the details, I didn't mention because already I felt the students already don't know yet the stratifications. To talk now about more than that, I think is pushing it a little bit.
Yes. When you consider R2 as a complex plane,
If you remember me, if you remember the example, so I can, because
yeah, the example was 1 plus z times the
yeah,
modulo of z squared. So this is not complex.
No, it's not complex.
Yeah, but if you look at the real part and then you take the complexification.
So I
There's
wrote
no problem.
z goes to 1 plus z. You write it in, so x plus iy goes to 1 plus x plus iy times x squared plus y squared. Yeah?
You can take the complexification. Can you say something about that?
Yeah, and then that means that you have to go with x, y goes to, and here on the first component you have 1 plus x times x squared plus y squared, y times x squared plus y squared.
So can you say something about this? Maybe. Okay, you have the theorem for complex germs, complex germs. But if you take the complexification in this case, can you say something in the real case?
No. I mean, what do you mean? So this is a map from R2 to R2, right?
Yeah, but you can consider, okay, now everything is complex.
You could. So your question is if I look at this map as seen from C2 to C2.
Yes.
Let me think.
No, C2.
I don't know if I can say right away. So the fiber is. I think this one is not a germ. Sorry. But I have to double check. So.
Okay.
You said something? Yeah, but I was saying that even if you don't have isolated singularities, you could still have an open mapping at a point. So that's there is not an implication. So yeah, this one doesn't have isolated singularity, but I think in this case it is not. I have to do some computations. It's not that simple. I mean,
Yeah,
to
yeah, yeah.
decide right away if it is a germ or not.
Yeah, and either way, if this is open at 0, if it were a germ and this is open at 0, this doesn't mean that the real part
So
is
if
going to
it's
be.
not open at 0, then it's not a germ.
Okay.
I said, if you have a map from CM to CP, to be a germ is equivalent to having complex structure, to be in complex, complex variety there of lower dimension. So if it is not a complex variety, then it's not, and if it's not open, not complex variety, it's not a germ.
Okay,
Yeah.
but still, if it is open at 0, it doesn't mean that the real germ is going to be open at 0. Yeah.
No.
So I want to comment that if you look to this kind of complex singularities, and if the singular locus is non-isolated, then the concept of Milnor vibration is not necessarily defined.
Yeah.
It's only defined for isolated singularities, as we saw in this morning lecture. But as soon as it's non-isolated, it's not always possible to have a good Milnor sphere.
Yeah, so I mean, that's why you have to put some, doesn't matter how you do it. You cannot get Milnor vibration for free just sitting in your, you know, you have to put something there and just.
Yes, I was wondering. I think it was a sufficient condition for having an NMG in the holomorphic case.
In the holomorphic?
Yes, it was a few slides ago.
What happens? Wait. Oh. Or you stop me when you see something that.
Yes, I think it's the next one because then you mentioned the real case.
No, so it's a complex case, right?
Yes. Oh,
this one?
No, it's I think one or two. No, farther up.
Farther, right?
I mean, not before, but after, yeah.
Sorry, where?
This one. Sorry, the previous one. Sorry, previous.
Back?
That's the one. That's the one.
Before or after?
No, it was slide 10. Slide 10. Yes.
Okay. There is there is not. It's not complex. This is worse for the real too.
Yes, that's what I was asking. Since the only additional conditions using this setting is that G is analytic, so I was wondering whether it would be derived from the complex case, taking the complexification of G.
No, so this you can do it directly from the definition. I mean, in the real case, you don't have to go to complexification. You just do it directly. Yeah, so it's not needed. The complexification is not needed.
Thank you very much.
Okay. Thank you very much.
Hello. Okay. In this talk, the idea is to discuss a local point view to K infinity F, consequently to the bifurcation set. So firstly, we recall the definition of BF, and after we'll want to discuss local point view to K infinity F at a neighborhood at infinity. So we recall here the definition of BF. So give you a map from Rn to Rp. We say T in Rp is a typical value of F if there exists a neighborhood U in Rp of T, such that the restriction of F to the pre-image of U over U is a C infinite trivial vibration. If not, then you say that T is an atypical value of F, and as before, we denote by BF the bifurcation set of F, and BF is just all the atypical values of F. We discussed in the first talk about BF and also about K infinity F. Before to state, you present some definition and notations. In this talk, we denote by Pn the real project space of dimension n. You use coordinates x0, x1, xn to any point in Pn. And we identify Rn as a subset of Pn with this identification. For each point in Rn, you consider this identification as a point in Pn. And you denote by 8 infinity all the points in Pn such that the first coordinate equal to 0. And it's just the hyperplane at infinity of Pn with the identification of Rn in this way. Now, give you a mapping from Rn to Rp. From this identification of Rn as a subset of Pn, you consider graph of F as a subset of Pn, and you define by X just to take the graph of F as a subset of Pn times Rp. So X is the closure of the graph of F in Pn times Rp. We denote by X infinity the intersection of X with the hyperplane at infinity times Rp. And we will go here the definition of K infinity. So given a mapping from Rn to Rp, we define in the first talk K infinity F as the points in Rp such that there's sequence in Rn, the norm comes to infinity, the image comes to T, and the norm of the sequence with V. dF here is the Jacobian of F in Xj. This product tends to 0. We'll remember here the definition of V. Star is the adjunct operator of the Jacobian of F. Far is a linear map from Rp to R, and you take this minimum for V. And with this set, we define the asymptotical critical point of f at infinity. So you fix a point in x infinity. Remember, x infinity is just the intersection of the close of the graph with the hyperplane at infinity times Rp. Then you say that P0 in x infinity is an asymptotical critical point of f if there exists a sequence in Rn such that when you consider this sequence at the graph of f, the limit is exactly P0, and also this holds. The limit is 2. The limits contain this product tends to 0. One example to illustrate the definition. So you take the same example from the first talk. We consider f from R3 to R2, defined as follows. If you take this curve, then we can compute f in the curve. This converts to 0 to the origin of R2. The limit converts to infinity. And we will have that this tends to 0. Consequently, by the definition of K infinity, the origin is in K infinity. But also, if you consider the curve on the graph of f, we have this identification for any point in R3. This is identified with this point in P3. When you take the limit, this converts to 0, 0, 1, so on. Consequently, by the definition 3, P0 is an asymptotical critical point of f. The idea is to give an interpretation to the asymptotical critical point at a neighborhood at infinity for this point. So we use some charts in PN, I will explain now. So given a map from Rn to Rp, we fix P0 in x infinity. And for simplicity, you suppose P0 like that, as follows. Then you consider the homogenization of Fi. Fi is just the coordinate function of f. And di is the degree of Fi for each I. Then you define Fi from Rn to Rp as follows. You take the homogenization of Fi. You use this coordinate system in Rn, y0, y1, yn-1, n-1. In particular, when you consider the origin of Rn, we have the identification with the point P0 in Rp. Di is just the degree of Fi. So you consider these functions for each I. And you say that f does not satisfy the t condition at P0 if there is a sequence outside the hyperplane y0 equal to 0. The sequence in Rn times Rp, and sequence in Rp plus 1, such that the limit converts to 0 T0. This, with the previous identification, this point is just P0. And if you take this combination, here is just the gradient of Fi. Here here we put var 0 in the first coordinate of this vector. This is a vector nk, which is a vector in Rn times Rp. And this limit converts to one vector as follows, with 0, 0. The first n coordinates are equal to 0, and you have a vector in Rp, so that Rp is not equal to 0. So we say that f does not satisfy the t condition at p0 if you have this behavior to the vectors. Geometrically, here some words. When you consider this coordinate system here, you can consider the function vi. So you consider z, for instance, z, as the intersection of the zero set of fi for I equal to 1 to p. This is a subset in Rn times Rp. And we consider G, yes, G, the function from Z to R, such that for each point in Z, y0, y1, n minus 1, t1, tp, this is just y0. Then in this way, the vector nk, since the gradient of fi is normal to z, each gradient of fi is normal to z, you have that this vector nk is the normal hyperplane of nk. This is a hyperplane in Rn times Rp. This hyperplane contains the levels of G. It means the restriction of G to Z. This contains G, the tangent space of yk tk, the fiber of maybe that. G, yk, tk. Then for each nk, you can associate to a hyperplane in Rn times Rp, just the normal of nk. This means that the hyperplane hk contains this tangent space. And you want to say what happens in the limit of this hyperplane. Okay, geometrically, this limit gives some information about the limit of the hyperplanes hk. So the main point here is that f does not satisfy the t condition, like that, if and only if P0 is an asymptotical critical point of F. Asymptotical critical point of F, remember that or exactly. We use the set K infinity F to define the asymptotical critical point. So you have a geometric interpretation to the K infinity F. Just an example to illustrate these definitions and to see how you can compute this condition. For instance, you consider F of x1, x2, x3. Just the example before, x1, x2 minus 1, x2 square, x3. So this is f1, f2. Then you take the homogenization of fi. This is just x0, x1. You take the homogenization that x1, x2 minus x0 square, and the homogenization of f2. This is homogeneous, so it's the same. Then you use this coordinate system here to define fi. So fi f1 is exactly, you take the same, but in x1 you take 1 here, and you x2 is y1, x3 is y2. So x1, x2, here 1 is y1 minus y0 square minus, the degree is 2, so it's t1 y0 square, and f2 is y1 square, y2 minus, the degree is 3, t2 y0 cubed. This is f1, f2, like that. Then you need to consider the gradient of f1, f2. The gradient of f1, you can compute that in the next slide. It's more easy, fast. This is the functions here, t1, y0. And when you compute the gradient of f1, is that. The gradient of f2 as follows. And you will consider this curve in R3 times R2 with the identification of each R3 to one point in P3. This curve is the same as before, but you use this change of coordinates, y with x. Then the gradient when applying the curve phi is like that here, and the combination of this vector we can take t and 1 over t cubed. Then the limit converts to a vector as follows. From the definition, just a second. From the definition of t condition, we have that the vector, the limit is like that in the example. So f does not satisfy the t condition at p0. This is just an example how you can compute the T condition at a neighborhood of P0. So just to finish, the idea is to talk a little about and to give some motivation about the bifurcation set. So you present 2 slides about the relation between the bifurcation set and the Jacobian conjecture. So we call here the Jacobian conjecture. So given a non-singular polynomial mapping from Cn to Cn, the Jacobian conjecture asks if F is an automorphism. This means that there is a polynomial mapping G such that the composition is the identity mapping. In other words, G is an inverse of F. This is an open problem conjectured by Keller, 39. And you have several results and reductions to the Jacobian conjecture. For instance, to show the Jacobian conjecture, you need only to show that F is an injective mapping. It's not necessary to show that F is an automorphism. So if F is a non-singular polynomial mapping, and the F is an injective mapping, then F is an automorphism. So one reference here is the book of Van den Ness, for instance. We have a lot of results and reductions in this book. And related to the Jacobian conjecture, you have the notion of non-properness set, is a topological set definition. So a mapping G is proper at Cn. We say that any mapping from Cn to Cm is proper at Y. If there is a neighborhood on compact neighborhood K of Y, such that the pre-image of K is on compact set. And the set of points at G is not proper, we denote by SG. And given a non-singular, this is the first relation between the bifurcation set and the Jacobian conjecture. If you consider a non-singular polynomial mapping, and the bifurcation set we define in the first talk and the talks of Joita is equal to the non-properness set of F, and in this case is equal to the K infinity F. And you know that F is an automorphism if and only if the bifurcation set of F is empty. So this is the first relation between the bifurcation set and the Jacobian conjecture. Like that. So to prove the Jacobian conjecture, we need only to show that the non-properness set or the bifurcation set is empty for any non-singular polynomial mapping. And the other relation with the Jacobian conjecture and the bifurcation set is the following conjecture. The conjecture 2 say if you take a polynomial map from Cn to Cn-1 for any n, if the bifurcation set of F is not empty, then the conjecture asks that any polynomial mapping, any polynomial function from Cn to C, this mapping has a critical point. So if Bf is not empty, then for any polynomial function H from Cn to C, there is this x in Cn such that the determinant of the Jacobian of Fa equal to 0 for some x in Cn. In other words, the mapping F8 has a critical point. Here the second relation between the bifurcation set and the Jacobian conjecture. The Jacobian conjecture is true if and only if the conjecture 2 is true. So you have these two relation between the Jacobian conjecture and the bifurcation set of polynomial mappings. I stop here. Thank you. Some reference here. Okay, thank you. Thanks.